Lots of time to practice. I'll point out, what you really need to know as we go. If you go on to real life, like in general chemistry and beyond, you need to know all this stuff. So that's why we're doing it all, even though you're not going to be tested on all of it. So let's just go ahead and do this.
All right, let's do it.
This is the mole concept. And that is Avogadro.
Who?
Avogadro. Avogadro is the champion of the mole. 1776 to 1856. When we talk about atoms in chemistry, we all realize that they're very, very small. A penny is about 28 sextillion. We talk about big numbers and small numbers all the time. In order to make doing calculations with numbers easier, chemists have developed what's called the mole concept. The mole is just a number, it's a unit. And it is 6.02 times 10 to the 23rd. When we talk about Avogadro's number, this is it, 6.02 times 10 to the 23rd. Now, Avogadro and others actually came up with this. Avogadro gets all the credit on it. Came up with this by making observations that suggested that equal volumes of any gas, contain the same number of gas particles. Didn't matter what it was. You have a liter of oxygen, a liter of CO2, they have the same number of particles in them. It was really surprising. Not only that, but if you took 22.4 liters of any gas, the mass of that gas equaled the formula mass of the element or compound. So this is really, really neat. Again, 22.4 liters of any pure gas contains 6.02 times 10 to the 23rd gas particles. Now, this means that if you have a pure substance and you simply add up its formula mass, now the formula mass is based on the number of atoms, different types of atoms, and their average atomic weight from the periodic table. You add all this up, you get a formula mass. If you have, let's say, carbon 12, the isotope carbon 12, and you have exactly 12 grams, that will contain 6.02 times 10 to the 23rd carbon atoms. Amazing concept. This is what we call the molar mass. This is what I just said. Exactly 12 grams of the isotope carbon 12 contains 6.02 times 10 to the 23rd atoms of carbon 12. Now, we know that carbon consists of isotopes. We've done that. When you add in all the isotopes, you get the number that's shown here for the mass on the periodic table, and that's about 12.01. So just for average mixed carbon isotopes, if you have 12.01 grams, you have 6.02 times 10 to the 23rd carbon atoms. Today we actually define Avogadro's number not based on volumes or anything like that. We define it based on carbon 12. So exactly 12 grams of carbon 12 is 1 mole. And anything that has the same number of particles is 1 mole. Now, it's important to realize that a mole is a unit, and we'll talk a bit about this. It simply represents a very, very large number, but it's a very convenient way to allow us to represent this. I need to pause for a moment because I forgot to do something here. Trying to connect. And a mole of anything is just a fantastically large number. Nonetheless, this represents 1 mole of the amino acid glycine. And you can literally hold this thing in your hand. It's, nothing at all. So a mole contains 6.02 times 10 to the 23rd things. Can be anything. When you think about a mole, you should think about the word dozen. We're all familiar with dozens. Dozens 12, right? Well, a mole is 6.02 times 10 to the 23rd. Just the number. This is the actual number, 6.02 times 10 to the 23rd. Again, 23 decimal places out there. Typically, we round it to 6.02. That's the number that you want to use. So, if we had 4-legged dogs, and we had 66 dozen 4-legged dogs, how many legs would we have? Let's solve this using the given ratio sort of thing. We're going to use that a lot. In this, we are given that we have 66 dozen, right? The ratio is 12 things in a dozen, right? We all know that. A dozen is 12. And every dog, by definition, is going to have 4 legs. So we could set this problem up this way. Start off with our number of dozens of dogs. Next, we need to convert dozen into an actual number. We can do that with the simple ratio, 12 things in 1 dozen. We also need to remember that there are 4 legs in every dog. So, dozen is going to cancel. Dog is going to cancel. And we're left only with legs. So 66 times 12 times 4, we have somewhat over 3,000 legs. Now again, that's a silly problem, isn't it? Well, let's do it in terms of moles. Let's say I had 66 moles of 4-legged dogs. We're going to do exactly the same process, except instead of 12 things in a dozen, we're going to say there are 6.02 times 10 to the 23rd things in a mole. So we start off with our given. Note that when we write moles, there are maybe 3 ways that we'll write it in equations and stuff. We can write out the full word moles. We can do M-O-L-E or just M-O-L. So you'll see them all, and I mixed them up for that purpose. So next we know that every mole is 6.02 times 10 to the 23rd things. And we know that every dog has 4 legs. So again, we're going to cancel moles. We're going to cancel dogs. And the only thing we have left is legs. Multiply it all out. 66 times 6.02 times 10 to the 23rd times 4. And now we're dealing here with three significant figures. So let's round this to 1.59 times 10 to the 26. Again, remember, a mole is just a number. It's a nice, simple ratio. 6.02 times 10 to the 23rd per mole.
Okay, Ross, where did you get the 26?
When you multiply 66 times this times 4, I think that's what you get.
No, she's asking the 26. Why was it 10 to the 23rd and now it's 10 to the 26?
Well, because we're multiplying by 66 and then by 4. So pull out your calculator and do it. But I think that's the right answer. All right, if I tell you
Okay, thanks.
a mole of hydrogen gas contains 6.02 times 10 to the 23rd hydrogen molecules, how many molecules will there be in half a mole? Again, we're going to do this with givens and ratios. Our given here is that we have half a mole, right? The ratio we're going to use is 6.02 times 10 to the 23rd per mole. Again, just like 12 per dozen. We start off with our given. Remember, we must have mole in our denominator. So this is nice and simple. 10 to the 23rd molecules per mole. Moles are going to cancel. And all we do is multiply 6.02 times 10 to the 23rd by 0.5. Now you see why I wanted you guys to learn how to use your calculators. I told you this was coming. When you do this, remember, we're just dealing here with the coefficient, aren't we? We're just going to divide this basically by 2. Do that in your head. It's about 3.01. 1 mole is 6.02 times 10 to the 23rd. Half of that is 3.01. We also use the expression mole when we're talking about formulas for compounds. Now we've written compounds like CO2. If we express that in the nomenclature of moles, what we could say is that every mole of CO2, same thing as every molecule, but every mole of CO2 contains 1 mole of carbon and 2 moles of oxygen. So we could say the mole ratio for carbon and oxygen is 1 to 2. Every mole of CO2 has 1 mole of carbon and 2 moles of oxygen. So it's just another way to look at a chemical formula in mole nomenclature. If we had ethanol, CH3CH2OH. In this compound, we have 2 carbons. So that would be 2 moles of carbon. We have 6 hydrogens, and we have 1 oxygen. The mole ratios would be 2 to 6 to 1. So let's do a simple problem. Here I have an ionic compound with 2 moles of iron and 3 moles of sulfate. go ahead and write the formula. Well, we have 2 moles of iron and 3 moles of sulfate, right? So, we just take our iron and our sulfate. If we have 2 moles of iron in every mole of compound, then this is simply Fe2. And if we have 3 moles of sulfate in every compound, we have sulfate 3 times sulfur. Now, what do you name this?
Iron sulfate.
Iron sulfate, except iron is transition metal. So we need the Roman numeral. Iron 2 sulfate.
It's on
I'm
two.
sorry, iron 3 sulfate.
I was gonna say, don't
Yeah.
you, okay.
Because there are 6 positive charges there and 6 negative charges. Iron 3 sulfate. Organic compound, 3 moles of carbon, 6 moles of hydrogen, 2 moles of oxygen. Go ahead and write it. Well, again, it's a very simple concept. If in one molecule we have 3 moles of carbon, that's simply C3, 6 moles of hydrogen, that's H6, 2 moles of oxygen, O2. Now we're going to use the concept of mole ratio several times in this chapter. So it's a simple concept. Again, it simply dissects the formula and converts it into mole nomenclature. All right. This is ammonia. We've all seen ammonia, NH3. How many atoms of hydrogen are there in 1,000 molecules of ammonia? Well, for this, you need to know your mole ratio, don't you? Every ammonia has 3 atoms of hydrogen. So our ratio is going to be 3 to 1. We are given here that we have 1,000 molecules. So let's start off with that as our given. We have 1,000 molecules. We have 3 hydrogens per molecule. Clearly, molecules are going to cancel. We're only left with atoms of hydrogen. And very simply, this is 3,000. Now let's do the same problem here in terms of moles. How many atoms of hydrogen in 1,000 moles of ammonia? Exactly the same procedure, except that we know that there are 6.02 times 10 to the 23rd molecules in a mole. So we'll start off with our given. That's 1,000 moles. Next, we need to convert this into the number of atoms. There are 6.02 times 10 to the 23rd molecules in every mole. So now we know how many molecules we have. And just like in the previous slide, we know that in every molecule, we have 3 hydrogens. So we can sit here and cancel our moles, cancel our molecules, and we're just left with atoms of hydrogen. Do our multiplication. We're going to do 1,000, multiply it by 6.02 times 10 to the 23rd, and then multiply it by 3. If you have your calculator out, you can play along. You should get about 1.81 times 10 to the 27. All right, so this is a very classic sort of question. Let's go ahead and look at another problem. Carbon tetrachloride. It's a molecular compound, so we have a multiplier. It's CCl4. I tell you we have 0.05 moles. How many chlorine atoms do we have in 0.05 moles? Try to sit back and set up your ratios. We're going to do this the same way. 4 chlorine atoms per molecule, and 10 to the 23rd molecules in a mole. Our given is going to be 0.05, isn't it? We need to convert moles into molecules. And then multiply that by the mole ratio, 1 to 4. So here's our given. Next we're going to put in Avogadro's number. That's molecules per mole. And next we have to put in our mole ratio, and that's chlorines per molecule. And that's 4. When we do this, we're going to cancel mole, we're going to cancel molecule, and we're left only with chlorine atoms. So once again, pull out your trusty calculator. 0.05 multiplied by 6.02 times 10 to the 23rd, multiplied by 4. When you do all of that, you should get about 1.204. We're dealing with 3 significant figures, so we'll drop that down to 1.2. Any questions? Simple use of mole ratio here to figure out the number of atoms in a certain number of moles of a compound.
I got 10 to the 23.
Yeah, I got 10 to the 23 as well, not 22.
Not 22 yet.
Really?
Yeah.
Oh, well, you don't have to show me. Well, maybe I made a mistake just to make sure that you knew what you were doing.
Okay.
Now we'll move to the next problem.
Okay.
Here I have 3.27 times 10 to the minus 9 moles of a gas. Okay? So, 10 to the minus 9 moles of gas. How many gas particles are in there? Well, here our given is going to be the number of moles that we have. And again, from Avogadro, we know that every mole is going to be 6.02 times 10 to the 23rd. That's our ratio. Simple ratio based on 6.02 times 10 to the 23rd particles per mole, and this is our given, our number of moles. Go ahead and write your ratios. Start off with your given. Our ratio is going to be 6.02 times 10 to the 23rd particles per mole. And again, moles is going to cancel. And we're just left with particles. Just like in the tutorial, take and multiply these two guys together. And when you do that, hopefully, you'll get 1.97 times 10 to the 15. Now, the good news is everybody's best friend right now are the tutorials, aren't they? And it turns out that there are tutorials dealing with mole conversions. So we're going to actually have 4 of them in this chapter. Mole mass relationships. Here we have a sample of potassium nitrite. NO2 is nitrite, remember? And it has 1.11 moles of potassium. How many moles of potassium nitrite are we dealing with? Now, think about this. You know how many moles of potassium you have? Potassium is K, right? Not P. You know how many moles of potassium you have. And what's our mole ratio here? 1 potassium per potassium nitrite, right? So frankly, we can just work this in our head. If we had 1 mole of potassium, we would have 1 mole of this stuff, right? So we're going to have, the answer is going to be 1.11. We know that. Let's look at the logic behind it. First of all, you need to find the mole ratio. The mole ratio is 1 to 1. This is kind of an important exercise because we are given moles of potassium. So when you set up the ratio, make sure you put moles of potassium in the denominator. That's the only way you can screw this up. So we know our number of moles, that's our given. Here's our mole ratio. Multiply them, and we get 1.11. Again, we could have done that in our head. Any questions? A sample of water contains 1.34 moles of hydrogen. How many moles of water is this? Well, again, the logic is going to be the same. We need to come up with a mole ratio of hydrogen to water. And clearly that's going to be 2 to 1. Our given here is hydrogen. So we need to make sure moles of hydrogen is in the denominator. So we would set it up like this. Moles of water, moles of hydrogen. Because again, our given is moles of hydrogen. When we do this, multiply this by the given, 1.34. Here's our ratio. We get 0.671. So half of it. Any questions? Simple exercise based on mole ratios. All right, let's look at an old test question. We have 17.8 grams of magnesium hydroxide. Now, the formula weight here is 58.32 grams per mole. How many moles is this? When you think about the ratio or the formula weight here, that's really a ratio, isn't it? This is 58 grams in 1 mole. That's a ratio. We are given grams, so we can set this up this way. We're going to take our mass here. We know our molar mass. Going to use that as our ratio. Here's our given. When we set up this ratio, however, remember, because our given is grams, we need to flip this upside down. Grams needs to be in the denominator. So we'll write it this way. 1 mole is 58.32 grams. That way our grams are going to cancel. All we're going to do is divide our mass by our molar mass. And when we do that, we should get about 0.305 moles. This actually is something that you need to, like, say to yourself as you fall asleep at night. Okay? Mass divided by molar mass is moles. Say that over and over again as you're falling asleep. Mass divided by molar mass is moles. If a mole is 6.02 times 10 to the 23rd, what's 10% of a mole? The reason I put this in is I want to stress to you what a percentage really is. Remember, when you do a percentage, you take a number, divide it by 100, that gives you a fraction, and then multiply it by 100. So 10% is really 10 over 100. So our given here is the number of molecules in a mole. 10% is simply 10 over 100. Take this, multiply it by our ratio here, and we have 10 to the 22 molecules. Now, which of these is the right answer? None of them are they?
None.
Everyone hates that.
Yes.
All right. I have yet another movie to show you. This isn't quite as cute or funny. It's a little awe-inspiring, however. As we do these calculations, we talk about big numbers, 10 to the 23rd. Most people really can't conceive a number that large. So, let's start off with an oak leaf. And we're 10 centimeters above it. What we're going to do is move out 10 to the 23rd places. So we start off right next to the oak leaf. We're out to 1 meter, 10 meters, 100 meters, a kilometer. At about 1,000 kilometers, you can see we're in Florida. There's the Earth. 1,000,000 kilometers, there it is, that's the moon. 100 million, here we are in orbit. 100 billion. And now at 1 trillion, basically we start to disappear. At 10 to the 18th, we're in this clump somewhere. 10 to the 20, you can now start seeing arms. And finally, at 10 to the 23rd, the Milky Way fades into a little blob in the distance. 10 to the 23rd is just a phenomenally large number. All right, we've been using the term formula weight. This is also described typically as molecular weight. It's the sum of the atomic weights of all of the atoms in a molecule. You also do molecular weight for ionic compounds, even though they're not molecules. But that's just what we do. If we had the amino acid glycine, and we saw this earlier, glycine has 2 carbons, 5 hydrogens, 1 nitrogen, and 2 oxygens. If we wanted to do the molecular weight of the glycine molecule, we would simply look at our periodic table. Carbon weighs 12.01. We have 2 of them. Hydrogen is 1.008. We have 5 of them. Nitrogen is 14. Oxygen is 16. So our calculation would look like this. 2 carbons, 5 hydrogens, 1 nitrogen, 2 oxygens. Multiply it out, add it up, we get 75.07. Again, this is the molar mass of glycine. If we have 75.07 grams of glycine, there are 1 mole of glycine molecules. Now, I know this sounds a little strange, but it really does work. This balloon holds exactly 1 mole of oxygen. Its mass is 32 grams. Oxygen is 16, it's diatomic. So that's 1 mole. This is 63 grams of copper. That's 1 mole of copper. 1 mole of water is 18 grams. 1 mole of calcium carbonate, chalk, is 100.09 grams. The reason that this is such a powerful concept is if we were going to react, say, oxygen with copper, we would know exactly what mass of oxygen to react with what mass of copper to make copper 2 oxide. This is how you do the calculations. It's the simple mole concept. All right, well, this is a strange problem. If I tell you I have 21 point blah, blah, blah grams of CO2, how many moles is that? remember what I just told you, mass divided by molar mass is moles. But pretend you don't know that. So let's go ahead and work this the old-fashioned way and set up our ratios and whatever. We are given a mass of CO2, aren't we? We're also given that CO2 has a molar mass of 44 grams per mole. And again, that's a ratio. So we want to set this up. This is our given. Going to flip our ratio over so grams is in the denominator. And simply solve our problem. Our molar mass is 44 grams. And we're trying to find the moles of CO2. Our given, 21.5 blah, blah, blah grams. Our ratio here, we flipped it upside down, so grams are in the denominator, and they're going to cancel. All we do is simply multiply this out, which is actually division. Mass divided by molar mass gives us moles. Now the reason I wrote this problem this way is to try to remind you about rounding. Remember we talked about rounding. How many significant figures are we working with here? 4. 44.01. So we have to round this to 4. So we're going to round here, aren't we? How is this going to round? Remember the rule? It ends in exactly 5. So how do we round it? Round it even. So 7.5 rounds to 8. If this had been 6.5, it would have rounded to 7. So just remember that rule. All right, let's do another one here. Here's a table. This is methane. What's the mass of 1.03 moles of methane? So step 1, go ahead and use the data in the table to calculate the molar mass of methane. Once you know the molar mass, go ahead and convert moles into grams. To get our molar mass, we have 1 carbon and we have 4 hydrogens. So multiply this by 4, add it to this. Our molar mass should be 16.0426 grams. Now I'm going to leave all these digits there. I'm just going to leave them there until we're done, and then we can round. So this is our molar mass. This is our ratio. We're given moles, so we want mole in the denominator. So we'll set this up this way. Here's our moles. We want moles in our denominator and grams up here in our numerator. And it's 16.04 to 1. When we do this, moles are going to cancel. Moles of methane cancel. And all we're left with is grams of methane. Our calculation, moles times our molar mass here, gives us this number, 16.5, blah, blah, blah. But how many significant figures do we have?
3.
3. So let's round this. It's going to round down to 16.5. Any questions? For our second tutorial on this chapter is moles and molar mass. So this should remind you of everybody's favorite density tutorial, where you have a table and you just have to fill in the missing value. This one, clearly you need to master. It's a very classic exam style question. Yeah. Okay. So here we're given mass, moles, and all we have to do is calculate our molar mass. Molar mass, remember, is defined as grams per mole. And by George, here we have grams, and here we have moles. So, all we have to do is divide our mass by the number of moles. When we do that, looks like it's about 100. That's right, again, remember this is your formula, mass divided by moles. Go ahead and solve for mass here. We are given a molar mass of 186. We're told that that represents 0.88 moles. What's the mass of our sample?
Is mass divided by molar mass, right? It's times. I mean, multiple.
Well, mass is going to equal the number of moles multiplied by our molar mass. Molar mass is mass divided by moles. Therefore, mass is moles multiplied by molar mass. All you have to do is plug in your numbers. Here's the number of moles, here's our mass, and we get 163 grams. Now there's another version of this tutorial that's essentially a word problem. Everybody says they hate word problems, but this is a word problem. How many moles does 87.36 grams of copper represent? Same sort of thing, it's just not in a table, is it? How many moles is this? Well, if 1 mole weighs 63.5, how many moles is 87.3? You're simply going to take your mass here, divided by your molar mass. Remember what you say every night before you go to sleep. Mass divided by molar mass is moles. Mass divided by molar mass is moles. So we simply take our mass divided by our molar mass, and we have 1.38 moles. Go ahead and do this one. What's the mass of 0.243 moles of lead? Well, we're looking for mass here. Remember, molar mass is mass divided by moles. Therefore, mass is going to be moles times molar mass. Our mass here is what we're trying to find. We have 0.24 moles, 82 grams per mole. This is 19.9 grams. Now this tutorial also has one other neat question. It's called Search Your Periodic Table question. We have an unknown element, and we have 29.14 grams of it. Somehow we figure out that this 29.14 grams is equal to 2.698 moles. So we're given mass, and we're given the number of moles. What's the element? Now clearly what you want to do here is solve for the molar mass, right? We have mass and we have moles. That gives us molar mass. Then you go search your periodic table for something that matches. Mass divided by moles is going to give us molar mass. Our mass here, 29 grams, we have 2.7 moles. We're looking at a molar mass of 10.8 grams per mole. So what you do is you punch up your periodic table. You can actually click the button and see one. Or you can just do that. Now you're looking for something with a molar mass of 10.8. What is it? B, boron. So in the tutorial, what you do is simply write just the symbol, and you get it right. Any questions?
So on this one, we should be rounding?
Well, I rounded because we only had 3 significant figures somewhere. I don't know. I rounded. Remember, the tutorials have a slop factor built in of 2 or 3%. So if you mess up rounding, it'll still give you credit. All right, let's do a slightly different calculation. Here we have a number of chlorine molecules. And we want to know the mass of this sample. How are you going to approach this one? Well, we know that 1 mole of chlorine would be 6.02 times 10 to the 23rd, right? So if we divide this guy by 6.02 times 10 to the 23rd, that'll tell us how many moles we have, right? And if we know the molar mass, we can calculate the mass. Here's our logic. We know the number of molecules of chlorine. We know molecules per mole, and we know molar mass. So we're going to have to set up three ratios here. Our given is going to be the number of molecules. The number per mole, that's Avogadro's number. And we have to make sure molecules is in the denominator. So 1 mole is 6.02 times 10 to the 23rd molecules. And finally, our third ratio is just going to be our molar mass. But again, since molecules are going to cancel, and if you're left with moles here, moles has to be in the denominator. Now we set it all up and we cancel molecules, cancel moles, and we're just left with grams. Once again, just like the tutorial on exponents, I'm going to take this number, divide it by this number, multiply it by this number. That's why you love your calculator. And when you do that, you should get about 0.011777, but we only have two significant figures up here, so let's round this to 0.012, or 1.2 times 10 to the minus 2. Here we have 0.2 grams of CO2. We want to know how many total atoms there are. So we're going to need a couple ratios again. We know our mass, that's our given. And we know our molar mass. So mass divided by molar mass is going to give us moles. Once we know moles, we know that every mole is 6.02 times 10 to the 23rd. And finally, we know that in every CO2, there are 3 atoms. So again, we're stringing lots of ratios. We know the mass. We know the molar mass, that gives us moles. We know molecules per mole, that's Avogadro. And we know atoms per molecule. So stringing is all together. There's our given. Next, we need to figure out how many moles this represents. Grams in the denominator. 1 mole is 44 grams. So this gives us the number of moles now, doesn't it? We know that every mole is 6.02 times 10 to the 23rd. Again, moles cancel, we're left with molecules. And finally, we have 3 atoms in every molecule. Once again, your trusty calculator, 0.2 divided by 44 times 6.02 times 10 to the 23rd times 3, 8.207, 2 significant figures, 8.2. Any question? Now our third tutorial kind of combines everything that we've talked about so far. Mole ratios and these very simple calculations. This is mole mass relationship. Here we're given a compound, lithium nitride. We're told that this contains 1.9 moles of lithium. We want to know how many grams of lithium nitride there are. Well, you need to use the mole ratio here first. We know moles of lithium, and there are 3 lithiums per molecule, right? So our mole ratio there is going to be 3 to 1. We know we have 1.9 moles as our given, and we know that lithium nitride weighs 34.8 grams per mole. So first of all, we're going to take this and our mole ratio, calculate moles. Once we know moles and the molar mass, we can calculate mass. Mole ratio, lithium and lithium nitride, that's 3. Lithium nitride to lithium, 1 to 3. Remember, I put lithium in the denominator because that's what we know. That's our given, moles of lithium. Has to be down here. So to get moles, we're simply going to take the number of moles, that's our given, and this ratio. We have 0.633 moles of stuff. Next, once we know the number of moles, we simply need to multiply that by our molar mass to get our mass of lithium nitride. Same sorts of problems we've been working. It just takes a little bit more thinking because you need to use your mole ratio. Let's look at another one. Here we have cobalt-3 oxide. A sample is about 0.6 moles of this. How many grams of cobalt do we have? Okay. Well, first, let's look at our mole ratio. We're looking at cobalt, so it's 2 moles of cobalt per mole of cobalt oxide. Moles of cobalt oxide are our given, so they're in our denominator, and our ratio is 2 to 1.
And you got the ratio because of the 2 cobalts, right?
Right, 2 cobalts to 1
To a
cobalt
one
oxide. All right, so we know our mole ratio. We know the number of moles. That's going to tell us the number of moles of cobalt. If we multiply these together, then we have about 1.2 moles of cobalt. Now we know that every mole of cobalt is 59 grams. So we just multiply the number of moles by our molar mass, and we get 70.7 grams. Let's do one more. That's an organic compound, C2H4O. Again, contains 4.2 moles of carbon. How many grams of our compound do we have? You should be able to figure this out now. Our mole ratio here is going to be 2 carbons for every mole of this stuff, right? So we're basically going to divide this by 2. That's going to give us moles of compound. Once we know moles of compound, and we know its molar mass, we can calculate mass. Looks like this. Moles of carbon has to be in our denominator, so it's 1 over 2. Again, we're going to divide it by 2. Our given is simply the number of moles divided by 2. We have 2.12 moles of our stuff. If every mole weighs 44 grams, 2 moles weighs 93.4. Any questions?
Please don't change it
I
yet.
won't change it yet.
It wasn't a question, but
All right, this tutorial is a little more challenging than the other 2, but still, I'm sure everybody here can do these with no problem. Tell me when I can change
okay,
it.
you can change it. Thank you.
Okay. All right, let's go and look at analysis, proportions, and things like that. Here we're going to look at ratios and look at problems and try to figure out how we can express these in terms of simple ratios. And then just use our simple algorithm. After we do that, we're going to move into chemical analysis and talk about percentage composition of compounds. All right. Percentage composition. I guess we're going to do it in the opposite, but that's fine with me. If we looked at HCl, and I ask you the mole ratio for hydrogen, everybody here can look at that and say, well, there's 1 mole of hydrogen for every mole of HCl, right? Now, if we look at our periodic table, we know that 1 mole of hydrogen has a mass of 1.008 grams, right? And if we look at our periodic table, the molar mass of HCl, that's H plus chlorine, is going to be 35.5. So if I simply write this as a mass ratio, this is exactly the same as saying 1 mole and 1 mole, 1 mole and 1 mole. It's a simple mass ratio. Now if we take this, because these are nice numbers, and we divide them, what do we get? 1 divided by 35. It's about 0.02. If we convert that into a percentage, make a percentage, we simply multiply it by 100 and stick on the percentage sign. We get 2.8%. Therefore, in terms of mass, HCl is 2.84% hydrogen. So what we've done here is simply taken the mole ratio, convert it to a mass ratio. Once we know the mass ratio, we can simply divide it, write it as a percentage, And we can say HCl is 2.84% hydrogen by mass. That's our percent composition. Calcium fluoride, CaF2. What's the percentage of fluorine? First of all, you have to do your mass ratio, or your mole ratio. It's 2 to 1, isn't it? 2 fluorines for every calcium fluoride. We look at our periodic table. Fluorine is 19 grams per mole. We add it up for calcium fluoride, and that's 78. Now we have 2 fluorines, right? So we're going to write this thing this way. 2 moles of fluorine for every calcium fluoride. Every fluorine weighs 19. Therefore, we simply multiply it by 2. The whole compound weighs 78. So we take our trusty calculator. 2 times 19 divided by 78. Multiply this by 100. By George, we're 48.67% fluorine. Everyone see that? Mole ratio to mass ratio. Do your math, multiply by 100, and you get percent. Yeah?
I guess I have a question. How did you get the mole mass for the calcium chloride?
For calcium fluoride, I have to add it up. I go to my table here, calcium is 40.08. Fluorine is 19 each.
Oh, okay, so you add those two. And
Add
that's
it all up.
Okay.
And that's 78.
Wait, you said he did.
But you times the fluorine by 2, correct?
Right. All right, let's do this.
He did it twice.
What is this stuff? Sc is scandium. Scandium is here. It's a transition metal. So what do we have to call this? Every chlorate is -1, so this must be scandium-3. And if you add up scandium-3, it's 295 grams per mole. So, the percentage of oxygen. How many oxygens are in here? 3 times 3. That's 9 of them, isn't it? Molar mass of oxygen is 16. This is 295. Set up a mole ratio, convert it to a mass ratio. Our mole ratio, 9 moles of oxygen, and every mole of scandium-3 chlorate. Every oxygen weighs 16, with 9 of them. 9 times 16 divided by 295. Simply do our math. Multiply 9 times 16 divided by 295, and you get 48.8%. Any questions? Let's do this just slightly differently. Just solve for something different. What if I tell you I have 454 grams of magnesium fluoride? How many grams of fluorine are in there? Well, for magnesium fluoride, we can go to our periodic table and simply come up with a molar mass, can't we? We have a mass, we know a molar mass. That's going to tell us how many moles we have. We know that in every mole of magnesium fluoride, we have 2 fluorines. So that's going to tell us how many moles of fluorine we have. And when we know that, we just multiply it by its molar mass, 19 grams per mole. There we go. Fluorine is 19 grams per mole. Magnesium fluoride is 62.3. Again, mass divided by molar mass is going to give us moles. Once we know moles, we're going to stick in our mole ratio to get mass of fluorine. There's our mole ratio, 2 to 1. Our percentage here then is going to be 38 divided by 62. Oh, not going to convert this to a percentage. I'm just going to use this as my ratio. That's right, because I can do that. It's just a ratio. Do it all at once. So for my ratio, I'm simply going to use the mass ratio. Again, grams of magnesium fluoride cancel, and we're left only with grams of fluorine. Very simple calculation now. 454 times 2 times 19 divided by 62. 276.9 grams of fluorine. Now comes our 4th tutorial for the chapter.
Oh, Lord.
This is actually everybody's favorite tutorial because once you get the hang of it, you can just buzz right through it. Just buzz right through it. Here, we are given a compound.
Oh, Lord.
What is COO? Hypochlorite, right? So this is nickel 2 hypochlorite. Molar mass is 161. Calculate mass percentage for all of these. All right, now think about this. How do you do this? Really is going to be your favorite tutorial. How do you do this? You look at this and say, what's the mole ratio here for nickel? It's 1 nickel per nickel hypochlorite, right? So that's 1. We know how much this stuff weighs. We know how much a nickel weighs. So, for nickel, it's simply going to be our 58.69 grams divided by 161. And we're 36%. So for chlorine, how many chlorines do we have? We have 2 of them, don't we? So we're going to take our 35, multiply it by 2, and divide it by 161. And finally, for oxygen, how many oxygens? We have 2. So 16 times 2 divided by 161, 19.8.
Okay, I can get with this.
Now, don't try to get ahead of yourself and figure you can only do 2 of these and then subtract from 100, because the math on the tutorial isn't that great, and it won't come out exactly right. Sorry, but it's close. So just go ahead and do all the calculations. They work nicely. Go ahead and do this one.
Can you go back for just a second, please?
I probably can.
Thank you. Okay, thank you. Thank you.
All right, look at this. Here we have calcium chloride. Right? Our molar mass is 175 grams per mole. For calcium, our mole ratio is what? 1. So we're simply going to take 40 divided by 175. And that's 22.9%. Now you're starting to see how this could be your favorite, right?
Mm-hmm. So easy.
How many chlorines do we have? 2 chlorines.
Just one.
Each one weighs 35. So it can be 35 times 2 divided by 175, or 40.5%. And finally, how many oxygens?
4.
We have 4 of them. So 16 times 4 divided by 175, 36.6.
And when it's like that, you can round up if you want, right?
Yeah. Once again, the tutorials give you slop around me. All right, let's go and look at some pretty pictures here for just a minute. Get all these numbers out of our head. All throughout the course, we've been looking at little molecular models. And, you know, I would just kind of tell you what they are and stuff like that. Let's just talk a little bit more about this. This type of a model is referred to as a ball and stick, because it looks like little balls and little sticks, right? A space-filling model is based on a calculation. What you do is you take the individual atoms and you calculate the electron cloud around them. And so the volume that is shown here represents 90% or so of the electron cloud. So this is a much better representation of what the molecule really looks like, but it's also very difficult to interpret because you can't see the bonds quite so clearly. The color coding that pretty much is used. Carbon will typically be black or gray or something like that. Hydrogen is almost always white. Oxygen is red, and nitrogen is blue. Then they kind of go with the color of the elements themselves. So sulfur is yellow, chlorine is green, bromine is brown. Basically just the color of the elements. This is bromine, again it's brownish. These are all of our diatomic elements. Now in our next chapter, we're going to be talking about chemical reactions. And it's important that you remember our diatomic elements. Because if I say something reacts with oxygen, it's going to react with O2, not O. So make sure you know all these guys, because it just makes the conversation much easier. The molecular formula, again, we've talked about how to do this. This is a ball and stick for our friend glycine. If we were to look at this ball and stick, using the color code we did before, we would say it has 2 carbons, it has 1, 2, 3, 4, 5 hydrogens, and 2 oxygens. So 2 carbons, 5 hydrogens, 2 oxygens, and 1 nitrogen. If we were to convert this into a molecular formula, we could simply say that this represents C2H5NO2. Now, this is a condensed formula. That's what it's called. The problem with a condensed formula is you can read this and it doesn't tell you a clue what the molecule really looks like. Therefore, we can modify this to kind of show the way things are stuck together. This is one way you could do it. Let's start at this end of the molecule. This is a nitrogen with 2 hydrogens. So we would start with an H2. This is bonded to a carbon with 2 hydrogens. So we put in a CH2. This is now bonded to a carbon with 2 oxygens and a hydrogen. We write that simply as COOH. So this tells us more about our molecule. Probably the best way to represent it, but it's much more of a pain, is what's known as a Kekulé statement, or Kekulé formula. Here we're going to write our NH2, more or less in Lewis style. So our nitrogen, here's our bonds. CH2 looks like this. We have a double bond to this oxygen, and then the OH. So this is a pain to write, but it tells you exactly what the molecule looks like. Condensed formulas really don't tell you much about the molecule at all, and the compromise is to string it out. We're going to use all of these as we do reactions. We also talked about empirical formulas in lab. Remember, empirical formulas are the lowest whole number ratio. This is glucose. Glucose is C6H12O6. The lowest whole number ratio for glucose is CH2O. Glucose is an example of a carbohydrate, isn't it? And that's where the name comes from. 1 carbon, 1 water. Now, empirical formulas don't tell you very much about your molecule at all. This is acetic acid, the acidic component of vinegar. CH3, COOH, but its empirical formula is also CH2O. Now, the little demo that we did in lab involved taking sugar and sulfuric acid. Remember, we dehydrated this. We removed the water, and we were just left with the carbon. In lab, they had powdered sugar, which was a very bad choice. Granulated sugar works much better. So here's a movie with granulated sugar. Same thing though. We're going to add our sulfuric acid. Stir it up a little bit. Slowly slowly it starts to turn black and ugly and get hot. And then, like magic, pure carbon is all that's left. And again, we're just simply removing the 6 waters and just leaving our 6 carbons behind. All right, let's just look at some empirical formulas. Very quickly look at these molecules and tell me what their empirical formula is. Remember, it's the lowest whole number ratio. Acetylene. Acetylene is what we burn in a welding torch. 2 carbons, 2 hydrogens. Empirical formula CH. This is actually a carbon-carbon triple bond between the 2 carbons. Benzene.
CH.
Sure, 6 carbons, 6 hydrogens. It's also CH. This is what benzene looks like. A nice flat ring, double and single bonds all the way around the ring. What's the empirical formula for water? Well, that is the lowest whole number ratio, isn't it? H2O. Hydrogen peroxide, however, we can divide by 2, and we get HO. All right, the second part of this, we're going to deal with proportions. Now, we deal with proportions all the time, even if we don't know it. And when we get to the chapter on gas laws, what we're talking about here is going to be very important. So let's pay attention. If we have 2 variables, say an x and a y, they have some value. They each have some value. There is always a constant that you can stick in to make x and y equal. There's always a constant of some sort, called a constant of proportionality. So we show it this way. Y is equal to some constant times x. And that's always true. Now, quite often we're going to pull this constant out algebraically and say that this constant is simply the ratio, in this case of y to x. Now, we've done this before. Density is a proportionality constant. It is simply reflecting the proportionality between mass and volume. So what we're going to do is use a ratio here, proportionality ratio, to solve very simple problems. Let's pretend that we have a mixture. We do an analysis, and we say that there are 3.4 grams of impurity, junk, in every 200 grams of this mixture. Okay, so we know that. If we have a 25-gram sample, how much impurity do we have? Now, the way we're going to do this is we're going to look at this and say, well, we have a ratio here, don't we? 3.4 grams to 200. That's impurity per mixture. So our given is that we have 25 grams of mixture. Our ratio is simply our 34 over 200. We have to set up this ratio so that mixture is in the denominator. When we do this, mixture is going to cancel, and we're left with impurity. We do the simple calculation, and this is 0.42 grams of impurity. So this is an example of a simple mass ratio that we're using here, impurity to sample. Now another example using a ratio like this is a simple percentage. We learned how to calculate percentage composition, didn't we? So let's say we did CO2, and you come up with the fact that this is 27% carbon. So you did that calculation, you did it. But if we have 255 grams of CO2, how much carbon do we have? Well, again, what we're going to do is set up a ratio based on our percentage. 27 out of 100. We have a given of 255 grams. Here's our ratio. Our given, our ratio, grams of CO2 cancel. 255 times 27 divided by 100, 68.85, and let's round it to 69, two significant figures. Now I put this little note in here, is the number of sig figs right? How many significant figures in 100? One. But that's not a measurement, is it? That's a definition. Percentage is a definition. So it's exactly 100 by definition. So it doesn't count. Only the experimental values count, and that would be 27 and 255.
And you get 27 over 100 because 27%.
27%, right. All right, one more. This is one of my favorite ones. Ever heard people talk about parts per million and parts per billion? You know, when you go swimming in the lake, they tell you there's so many parts per million bacteria in there, and you shouldn't swallow whatever you do, et cetera, et cetera. Well, part per million and part per billion are simply ratios. What it means is 1 part of something per million parts of something else. So, everyone knows that tuna, because it's a large, oily fish, can accumulate mercury. So let's say that you went to a sushi bar, and they had a sign up that our tuna for today has 988 parts per million of mercury. Do you eat the tuna? Well, how do we solve for this? We have 100 grams in our sashimi order. Okay? 100 grams. We know a ratio, 988 mercuries per million grams of tuna. Doesn't sound like much. It would look like this. 988 grams, million grams of sushi. We're eating 100 grams, our sushi cancels, and we're left with 0.0988, about 0.1 grams of mercury. In the multiple choice question, I'll pause for a moment. In the multiple choice question, we simply want to pick out 0.0988 grams of mercury. The realization is lethal toxicity for methylmercury is 20 milligrams per kilogram. So if you weigh about 70 kilograms or so, that means you would have to eat 3 pounds of the sushi to kill yourself on the spot. And you'd probably die from the 3 pounds of sushi, but I assure you that eating 100 grams would make you really, really sick. Really sick. All right, the tutorials we did for today. These are the names that are on the site, okay? Converting between moles and mass, mole mass conversion to mole mass formula, and calculating percent composition. Make sure you do them. They're everybody's favorite thing to do. All right, I hope you know, well, it doesn't look like there's much snow out there at all. So.
No, actually it doesn't.
Yeah, that's good. All right, today's
Molar
Wednesday.
mass quiz, we don't do that, right?
The what?
This molar mass quiz.
You don't get credit for it, but I would do it, of course.
Okay. Monday, you hand it back to the Oh, give me those boots, girl. You didn't hand back to the
Yes,
I need to go to the
You got that?
yeah.
I need to go to the bathroom.
I don't know if I have them with me.
I've been wanting to.
Oh, I do. So,
Adam?
Adam?
Yeah. Probably the nice one, yep.
There we go.
And then I the only one I have to do is just this one. I'm still gonna do that. Just so I can get the
I'm
credit.
gonna do it.
Cause I have to see. No,
Not
I
that.
gotta find, cause I have an extra one, but I don't know where the freak it is. My brother. Oh my God, these things are expensive. That's why I was so. It's like 100.
Yes, I don't have to say expensive. We only just wait, cause we're moving.
Oh, so you got.